So this is very similar to if you are in AP Physics with Miss Armbruster. She is doing extra credit elf on the shelf. Okay, I am doing extra credit gnome on the shelf because I didn't have an elf on the shelf. So this little gnome guy will be roaming around the halls, or not the halls, but roaming around the classroom, okay? When you come in the next 6 class periods after today, you will find him, you will take a picture of his problem, and you will solve it so that you can get extra credit, okay? This document is in Schoology, so you can go grab it in Schoology. It's called Gnome Elf on the Shelf. I will not be posting these problems anywhere, so if you are gone for a day, ask a friend, phone a friend, tell them to send the picture to you so that you can get the extra credit if you would like it. Now, do we have to do this extra credit? No. Would it be silly to not do the extra credit? 100%. Do not come to me say, oh, I really wish I could have an A and I'm at an 87%, but I'm not going to do the extra credit. Okay, that's not going to happen. Here is your chance to kind of buffer you from that, you know, if you're on like a cusp of one of those letter grades, okay? So there's a little poem over here. You can read it if you want. But basically, the first question, okay, is he was actually entangled in an equation here, but I unraveled it for last class. This equation, you need to uncover the derivative at the point marked with a star. So if you would like to come up here, take a picture of this problem, you will show all of your work on this document. The last thing that I was going to say before I have you come up here, you'll fill in all of your stuff on here. Make sure you have all of your work shown. If you don't have all of your work shown, I will not be giving you points for it. If you just write a number down, that's not going to be how, I'm not going to give you points for that. Miss Armbruster is taking them every day. If you would like to turn them in, I'm going to wait until the very end. So there is a spot on Schoology that you can turn in all 7 or all of whatever you completed. You can turn those in on Schoology as well. Okay, questions on that? Okay, we will not be doing these in class. So these are for you. These are going to be kind of problems, not necessarily what we're doing right now. There might be some problems like that, but they're going to mostly be problems that we've done like the past few tests to kind of help bring a few things back. So you might need to go back and look at notes of how to solve some of this stuff as well, okay? So if maybe 1 or 2 of you around want to come up and take a picture, and then you guys can just share it with each other, or however you want to do it, come up and take a picture of these problems so you can have those for the first puzzle to get those extra credit, okay? Okay, so this little activity here is designed to help us figure out kind of the second derivative and what it tells us about a function, okay? So I've got a function up here. We're talking about influenza outbreaks, or how fast does a flu spread. This is our function f of t, okay? And that tells us what the population of people that have the virus is at a certain day after day 0, okay? So this graph is 21 days after the start, or after the outbreak of the flu, okay? So first thing I want you to do, talk to your neighbor about what is happening over this 21-day period of people that are infected with the flu, okay? You can talk about it. You don't need to write it down, but talk about what is happening at day 1 versus day 22, or what's happening as you go from day to day on this graph. What do we think? Does someone want to raise their hand and share with us what they think is happening from day 1 to day 22? Yeah.
I think it increases slow and then very fast and then slow again.
Yeah, I love it. Increases slow, increases really fast, and then increases slow again. That's great. Anything else? Anyone else want to share? I mean, that's a pretty good explanation. So I like it. So let's keep going here. Number 2, it says, when is the number of infected people growing the fastest? How do you know? So like she was just saying, it grows really, really quick, right? Where is that about in between? What values? 6 to 16. Okay, could we make that a little bit shorter? Because it looks like if I'm talking about specifically how fast things are growing, or what the rate is at a certain point, you're looking at like the slopes, right? So like, is the slope at 6 really as steep as the slope over here? No. So let's like make that interval a little bit smaller. Where is it happening the fastest? 9 to 14. So is from 9, let's see, 9 and 14. 14 looks pretty steep compared to 9. I mean, again, it's kind of hard to tell. Anyone else have a maybe smaller interval there? 11 to 12, right in between these 2 points is actually the steepest, or the fastest that the rate of people infected is growing. So we can say in between day 11 and 12. Okay, that's because our slope is the steepest. Now, we're going to get some practice evaluating derivatives on our calculator again. And if you forgot how to do that, that's okay, because I'm going to show you. You are going to go to Math, option number 8. It says N derive. Okay, so your calculator should look something like this. D over D box times a box, and then evaluated at a number. Okay, so inside this first box, I want you to always choose the variable x, and I always want you to choose the variable x here. Okay, don't choose anything else, because then your calculator might get a little angry at you. In this first parentheses there, you are going to type the function that we are evaluating it at. So the function is the 1,000 divided by 1 plus 999 e to the negative 0.6030x. Okay. If you would also like to assign this a variable, kind of like what Jacob was saying, if I wanted to say this was y1, then I would just type y1 into those parentheses there. Either one is fine with me. And then all I want you to do is you are going to evaluate this table. So we're basically looking at certain values on this function, f of x or f of t, at these values of 3, 5, 9, 11, etc., etc. Okay? So I want you to plug in this box, all of your values, all of your numbers go in there. And then you can just go back up and change each number. Yep, you'll have to do one at a time. So start with 3, then 5, then etc., all the way up until 20. Okay? So I would not retype it. I would use your arrows and then go back and hit enter and then just change the number that you're evaluating at. Okay? So for the first one, just to make sure we're all on the same page, you should be getting 3.64. Okay? 2 or 3 decimal places is fine with me. But go ahead and evaluate from 3 to 20. And if you got questions, I'll come around and help you. So now to find the second derivative, on our calculator, we are going to do one of two things. Okay? One of the ways to do it is to just evaluate the derivative. And then once I know what the derivative is, instead of plugging this in, instead of plugging this value in, I could plug in my derivative, and then it will take the second derivative, because it's basically taking the derivative of the derivative, right? Okay? So that's one way to do it. Another way that we figured out how to kind of hack the calculator is we're going to type in exactly what I have over there on the board. I'll write it on here as well. But you're going to type d dx, and then in the parentheses, you have to type d dx again, and the function that you originally typed in, the 1,000 over 1 plus 999 e to the negative 0.6030x. And you're going to evaluate that at x equals x, and then actually evaluate it at the number. So x equals, for the first one, we're going to plug in 3, but this number is going to change, okay? So again, this notation is taking the derivative of our function, aka the second derivative. Okay, so this thing right here tells us f double prime of t, evaluated at a certain point. Okay, so try typing that in. If you type in 3, you should get 2.168. Okay, so if you do not get that, let me know. I'll also write the second one. You should get 6.842. Okay, what I want you guys to talk about right now is the following two questions. What values is my derivative increasing? And what values is my derivative decreasing? How do I know? That means we're only looking at the first derivative right now. We're not looking at the second derivative. When is it increasing? When is it decreasing? We talked about this last class. How do I know? And then number 5, how can I look at the graph and decide when is my function increasing and decreasing? Okay, talk about that, write down some answers, and then we will come back together. So for when is our derivative increasing, looking at our table, if I look at my table, the values are increasing all the way until I get to what? Yeah, 11 is when it stops, right? And then they start decreasing. So it is increasing, or f prime is increasing starting at 0 and going up until 12. Okay. The derivative is decreasing from 12 all the way to 22.
22.
Or is it 21?
It's at 20.
But on the actual graph. If I look at the actual graph, we only evaluated the points at 20, but it does go all the way to 22, right?
Yeah, it's starting to...
So if I go back and look at this graph, okay, in between 11 and 12, somewhere in between these 2 points of 11 and 12, it's flipping, basically, okay? There is a certain point in between this, and it's called the inflection point, okay? It's the point when my derivative changes from increasing to decreasing, okay? So we're actually going to change this, not to 12. We're going to change it to, we're just going to kind of eyeball it, approximately 11.5. Maybe. Okay? So that's our inflection point, and an inflection point basically is when our derivative changes from increasing to decreasing, okay? So if I look at my graph, if I go back up here and look at my graph, okay, to tell when is my derivative changing from increasing or decreasing, there is this kind of test that we can do called concavity, okay? It's looking at when is the graph concave up versus concave down. Now, concave up is, think about like a smiley face or like a valley, okay? So something like this is concave up. Everything to the left of that point is kind of like a smiley face, kind of like a weird sideways smiley face. Or think about, you can fill that, right? Like a valley, you can fill that with water, yeah? So this would be a concave up side. Concave up. Now, concave down, okay, that means your kind of parabola shape is pointing upside down, okay? Or it kind of looks like a frowny face, or think about it like you're going over a hill is when it's concave down, okay? So this side of the graph is concave down, okay? So at this point here, our inflection point, it changes from concave up to concave down. And that's how we'll be able to tell on our function graph. See you later. On our function graph is when we have that point of inflection here. Let's also label that on here. That's our point of inflection. When it changes from concave up to concave down. So let's go ahead and write down some information here. So from 0 to 11.5, f of t is concave up. Okay, think smiley face or valley. Okay, then from 11.5 to 22, your f of t is concave down. Think sad face or mountain or hill. And when we look at the concavity, we're looking at the second derivative, okay? So concave up is actually when my second derivative, so f double prime of x, if I go back up here and look at my second derivative, all of these numbers, when it's concave up, so that first piece there is concave up, it's concave up when all of my second derivatives are what? Positive, okay? So it's concave up when they are positive. I kind of switched the colors here, but that's okay. So when it is greater than 0. Then it's going to be concave down when it is less than 0, okay? So this is when f prime double prime of x is less than 0. Okay? So moving forward, when we know something about the function, or if we know something about the derivative or the second derivative, we're able to say things like, if I know that this second derivative here is greater than 0 when it's concave down, I know that this slope, the slopes are starting to decrease there, okay? We can also talk about, like, the actual function is still increasing, but the derivatives of all those things are starting to decrease there. So we're going to have to be able to, next class we'll spend more time kind of comparing all three of them together and how do I go from one to the other, but today we're going to specifically talk about the second derivative, okay? So let's look at some examples. I'll write down a few notes. Some important ideas about our second derivative, okay? Our second derivative, so our f double prime of x, is telling us how our slopes are changing, okay? So is how f prime of x is changing, or how the slopes of f are changing. If we know that the derivative of x, second derivative, is greater than 0, that also tells us that our first derivative is increasing, which also tells us that f of x is concave up. Our second derivative, if it's less than 0. If it's less than 0, that is because our first derivative is decreasing, or our f of x function is concave down. So again, given any one piece of information in this line, we should be able to fill out the other two. If you just know that the function is increasing on that interval, you know it's concave up and you know that the second derivative is greater than 0. If I said, okay, well, the second derivative is less than 0, you should be able to tell me that the function is concave down and that the derivatives are decreasing. Okay, so we should be able to kind of fill in the blank if we're given one of those pieces of information. Yeah. Next thing is our second derivative, our talk about inflection points. That point kind of where it changes, where your derivatives are increasing versus decreasing, is kind of where that S happens on your curve, okay? So when my second derivative is equal to 0 or undefined, and, keyword here, and, the sign changes. So they change signs when we're looking at our sign chart. So if it changes signs, then we know that our derivative has a relative maximum or minimum, and we know that f of x has an inflection point. And that is all we'll put in this box. We'll talk about second derivative test next class since we ran out of time in my previous class, so we won't get to that today. So let's look at an actual example of this. If I'm given a function, okay, these are usually going to be like questions that you're probably not going to be able to use a calculator for. Because if I could just graph this, do you think I could probably tell where it's concave up versus concave down?
Yeah.
Pretty easily, right? But you have to do it analytically by hand. Okay, so the first thing that we need to do is we need to set this derivative well, the second derivative equal to 0. But first thing I got to do is find my first derivative. So what's my first derivative here? 3x squared minus 12x. And then if I take my second derivative, 6x minus 12. Okay, not rocket science here. But when I am finding this point of inflection, I got to figure out, well, when is that equal to 0? When is the derivative equal to 0, or when is it undefined? Okay, so set this equal to 0, and we get x to be 2. Okay, at this point, okay, this is a possible point of inflection. We have to test to make sure that the second derivative is changing from a positive to a negative in order for it to actually be a point of inflection. Okay, so I'm going to make a little sign chart here. And on that sign chart, I'm going to just put the number 2. And I'm going to label that this is my second derivative sign chart so that I know when I'm testing points, I'm plugging points back into my second derivative. Okay, so I'm plugging points back into this function right there. So to the left of 2, if I plug in 0. Plug in 0, are we going to get a positive or a negative value there? Negative, because 6 minus 12 is negative, right? If I pick a point to the right of 2, let's pick, I don't know, 3. If I pick 3, 6 times 3 minus 12, what's that give me? Positive. Okay, so that point at x equals 2 is a point of inflection because the second derivative changes from negative to positive. So we can go ahead and say that this point right here is a point of inflection. Oh, and actually what I care about is concavity, so I don't care too much about that point of inflection, but I do care because I need to test, well, when is it going to be negative, okay? Because concavity for down is when is my second derivative less than 0, okay? So 2 is in fact a point of inflection, but we know that it's concave down when we have less than 0 for my second derivative. So I can go ahead and say that on the interval from negative infinity to 2, or you could also say when x is less than 2, f of x is concave down because our second derivative is less than 0. That's your justification. Let's look at number 2 here. Number 2, if we're given the derivative function, we're figuring out what values does my g of x have a point of inflection, okay? Well, it's already given to us of our derivative, so we don't have to do any driving, but I need to see, okay, well, when does this whole thing, when does that equal 0? What x values is that going to make equal to 0?
3, -4, and 6.
Yeah, 3, -4, and 6, and you find that by setting each factor equal to 0. X minus 3 squared equals 0, x plus 4 equals 0, x minus 6 equals 0. So my values that I'm checking are x equals 3, -4, and 6. And I found that when my second derivative is equal to 0. So I got to test these points again. I'm going to test the point, let's see, -4, 3, and 6. So I've got 4 intervals there. This is my second derivative, so I'm going to label that sign chart so I know what that is going to tell us. That's going to tell us about concavity and points of inflection. So plugging back into my second derivative function, I care if it's positive or negative. So let's pick a point to the left of -4, maybe -5. If I pick the point -5 and I plug it back in, I'm going to get a positive times a negative times a negative. So that would give me a positive for that one. Okay, let's pick a point in between -4 and 3. What's the best point to pick? 0. If I plug in 0, I get a positive times a positive times a negative, so I get a negative. And lastly, or not lastly, actually, we got 2 more points to test here. In between 3 and 6, pick a point, and in between 6 and infinity, pick a point. Plug it back in to see what your sign is. Negative here and positive here, we all agree? Nice job, okay? So looking at these kind of critical points here, we're trying to see which one is an inflection point, okay? The one that is an inflection point is when it changes from positive to negative and it's when your x value is equal to 0, or sorry, when your second derivative is equal to 0. So this value here changes from positive to negative, right? And then what other x value changes from negative to positive? 6, right? So 3, however, is not an inflection point because it does not change from positive to negative or negative to positive, okay? But it is a point that we needed to test to see if it was a point. It was a possible point of inflection. Does that make sense? Okay. So we can go ahead and answer this by saying which values of x does g of x have an inflection point when x equals -4 and 6, g of x has a point of inflection. Because it does say justify. Because our derivative, our second derivative, changes signs. You might be asked to actually find the specific point of inflection, okay? Which means if I have an x value, how would I find the y value at the point? Plug it in. Specifically, plug it back into the regular equation, okay? This one doesn't ask us for that because we were only given the derivative, the second derivative, okay? So I can't actually find the exact point, but I can tell you the x value where that point occurs, okay? All right. Next one's kind of just to check to see if we understand the notation and just to make sure we understand concavity versus derivatives, first derivatives. So we've got a graph. It's the f of x function, okay? There are 4 points labeled on here, A, B, C, and D. We are looking at first, when is the derivative greater than 0, okay? So you're asking yourself, when are the slopes positive, right? The second piece here is we're asking ourselves, well, when is the second derivative less than 0? Okay, if it's second derivative, we're looking at concavity of the original function. So if I'm given the function f of x, we're looking at when is this concave down, okay? So go ahead and label on your graph those two things, and then we need to figure out where is the overlap, okay? Because it's asking us to determine the intervals where those both happen, okay? I want to find where does this and this happen on. So go ahead and label those on your graph and figure out what you think the answer to this one might be. And we are also not doing number 4, so you can cross that out. So slopes are all going to be positive. If I look at all the tangent lines here, positive, 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 where do the slopes stop being positive? At C, right? At C, this slope of that tangent line is 0, right? And then those slopes change and those slopes become negative for all those things, right? Okay. But then, so everything to the left of C, so A to C, has slopes that are positive, okay? So I'm going to say from the interval A to C for that. Now, concave down, we're looking at kind of where does it switch from going up to going down there. At this point right here, what's the point that it's changing? Where's that inflection point? B. B is our inflection point. And if I go ahead and highlight this piece here, from B to D, looks like a frowny face or a hill, right? That's when it changes from your valley to your hill. So our concavity down is from the interval B to D, right? So where is both of those things? Where is the overlap? B to C. So my answer for this kind of question here is from B to C. So from B to C, I'm just going to put arrows there because that's our justification right above there, okay? From B to C, both of those things are true, okay? It's both having your first derivative be positive and your second derivative be less than 0 or negative. Okay? Only other thing I want to point out on this paper is when it says twice differentiable, that means you can take the derivative 2 times, okay? Differentiable means you can take the derivative of your function and then evaluate some things based on that, okay? All right, let's go ahead and head to a few examples. And again, we're not doing everything. We are doing some of it. Okay, like right now, we're going to cross out example 2 right now. Okay, we're going to talk more about graphing next class and how to graph functions, derivatives, second derivatives. What do those functions all look like in relation to each other? But let's go ahead and start out with example 1 here. We've got a function f that's shown below. State what the signs of f prime and f double prime are on the interval from 0 to 3. Okay, so I want you to fill in 2, or actually maybe 3 blanks here, okay? We can say that f prime of x is either, don't shout it out loud, but think about it for a second, is either increasing or decreasing on the interval from 0 to 3. Okay, f double prime of x is, let's see. Actually, I want to say you're going to fill in the blank less than or greater than 0. Okay, making, f of x concave up or down on the interval from 0 to 3. Okay, so I want you to try filling in the blanks before I tell you what they should be. F prime is blank on 0 to 3. Increasing or decreasing goes in that blank. I wrote this wrong. This should just be f of x. F of x is increasing or decreasing on that interval from 0 to 3, which means that my first derivative here is either less than or greater than 0. That's what I wanted to write, sorry. And then our second derivative is either less than or greater than 0, making our function, which is drawn here on the left, concave up or concave down. So our function, is it increasing or decreasing on this interval? It is decreasing, okay? So when our function is decreasing, our first derivative is less than 0, right? If I look at all these points of all these tangent lines, all of those slopes are negative, yes? Okay? Our second derivative, when our second derivative is greater than or less than a number, we can figure out if it's concave up or concave down. Let's first say, is this concave up or concave down? It's concave up, okay? If I look at this, it looks like I'm going down into a valley, or it's like the start of a smile. Or wait, you just said down or did you say up? You said up, okay, good. Yes, concave up, okay, smiley face, you're happy, right, going down into a valley. It's a lot easier of a hike than going up into the hills, yes? Okay, so this would be concave up on that interval, which means that my second derivative is greater than 0. Again, we'll skip the graphs for now, but let's look at kind of, if we're given a function, again, how can I figure out all these things algebraically? Okay, so we're going to figure out the intervals when it's concave up or down and find the points of inflection. So first thing that we need to do is find the first and the second derivative. These are nice and easy. First derivative would be 4x to the third minus 12x squared. What's my second derivative? There we go. So I need to figure out, where is this equal to 0? When I set this equal to 0, it's going to allow me to figure out where are my possible points of inflection. They are not assumed to be points of inflection until after we test the intervals. So I need to set this equal to 0. If I set this equal to 0, factor out a 12x, I'm left with x minus 2. What are my x values going to be?
0 and 2.
0 and 2. Okay, these are possible inflection points. So now I've got to test our values. So I'm going to go ahead and create a sign chart. And this is for my second derivative. The points I'm going to put on there are 0 and 2. And when I test a point in any of these intervals, I am plugging it back in to my second derivative. Okay? So go ahead and pick a point to the left of 0, in between 0 and 2, and then to the right of 2, and find out, are those values going to be positive or are they going to be negative? Okay, go ahead and do that real quick. Did we all find that it should be, in fact, positive, negative, and positive? Yes? Okay, very good. Again, you're testing those points back into your your second derivative function. Okay? Now, once I've got these values, I know that this point of 0 and 2 are going to be points of inflection, not only because it makes my second derivative equal to 0, but because my sign changes from positive to negative. Okay, so we can go ahead and say that at x equals 0 and 2, we have actual points of inflection. Can I actually find out exactly where that point is? Yeah, I can plug that back into my function, right? So let's evaluate f of 0. If I plug in 0 into my function, I get what? 0. Okay? So the point 0, 0 is an inflection point, and then I can also plug in 2. If I plug in 2 into this function, plug that in my calculator. Oops. Who's quicker than me? -4 times 2 to the third. I got -16. Perfect. So, and the point 2, -16 would also be an inflection point. So we can say that 0, 0 and 2, -16 are inflection points because our second derivative changes signs at x equals 0 and x equals 2. Okay, we can also talk about concavity as being concave up or concave down. So concave up happens when what? My second derivative is positive or negative? When it's concave up?
Positive.
Positive, right? So everything to the left of 0 and to the right of 2 is going to be concave up. So I can say that either by using intervals or saying x is less than 0 or x is greater than 2. But I'm going to say concave up from -infinity to -1 and 2 to positive infinity. Oh, sorry, I meant to say 0, didn't I? All the way to 0. And we know that because my second derivative is greater than 0. We know the function is concave down when it's in between 0 and 2, or when my second derivative is what? Negative, right? So concave down from 0 to 2 because my second derivative is less than 0. And let's look at example C. So, unfortunately, we've got low D high minus high D low derivative coming at us, not just once, but twice. Okay, so I've got to take not the first but also the second derivative. Okay, so I'm going to give you a chance to try it out first. Make sure you simplify your derivative before you take the second derivative. It'll just make your life a little bit easier because hint, hint, things are going to cancel out. And then once you get to the second derivative, simplify as much as you can, and then we'll go from there, okay? Okay, once you've tried out your first derivative, I have the first derivative up there simplified. Okay, after you have done the first derivative, go try the second derivative. And then I will go through that here in a few minutes as well. Again, you don't have to simplify this denominator, but I think it might just be a little bit easier if I simplify this denominator as x to the fourth minus 8x squared plus 16. And then I'm going to take the derivative of that. So follow along, make sure you got the same thing as I did. If you did not simplify that, you just have to make sure you did the chain rule for this term right here. Okay, so I've got low d high minus high d low all divided by low squared. Okay, and now I'm just going to simplify some stuff here. Distribute that negative 10. And then I'm going to distribute, let's see, this negative 10x minus 40x squared. Oops. I made some mistakes last class when I was doing this, so I'm going to try and not do that this time. It should be to the fourth power. I'm just going to write x squared minus 4 to the fourth, because that's technically the same thing as this, right? Squared. This is,
They did the derivative. Why is it squared there, not just 16x?
yes, this should just be 16x, thank you. And that would just be 16x squared. Good catch. Okay, then if I combine some like terms here, I'm going to get negative 10x to the fourth minus a negative 50x to the, or sorry, minus a negative 40x to the fourth. So that'd be plus. So it's actually 30x to the fourth. And then I'd have 80x to the second minus 160x to the second. So that's a minus 80x squared. All divided by x squared minus 4 to the fourth power.
That was easy.
Yeah, okay. I still feel like I made a mistake somewhere. What the heck? Oh man, this is what I get. Because I should have ended up with 30x to the fourth, or 30x squared plus 20, or 30x to the fourth minus 80x, just minus 80. What the heck?
Did you not do the math?
Apparently, well, I did it slightly differently than I did last time, and I still made a mistake, so I thought this way would make less mistakes, but apparently I still made a mistake.
Are you sure the answer you had is wrong?
No, I'm sure the answer's right. But, oh wait, no, wait. Minus, we're good, sorry, we are good, this is correct, okay? Let's see.
Yeah, how do you change the
Poly root finder. You just move over your arrow to the fourth one.
for order?
Yes. That was the first thing in there, right? Yeah, it says order. If you put what? Sorry.
Put 0 or 1 for the 8 out of 3.
0 or 1 for the 8 of the.
I tried to get it. I know big W. Everyone does celebrate. Yeah, everyone does celebrate.
Okay, did you guys get it on your calculator? Plugging it in?
It's a great news.
What'd you say? Yes, question, Steve? No, you got it? Okay. Where are you going?
For business vlog.
December 6th,
That's
Wednesday.
next class.
Yes, just make sure you watch the video.
Yeah, I will.
Okay. I believe it. Where are you guys going?
Core room.
Ooh, exciting. What do you have, A?
Yeah.
I love how they put the logo over this so you can't even see what I wrote.
I know.
6 periods. Schoology. But like, you have to watch the video. Otherwise you're going to be lost.
Yeah,
Okay?
I
Okay.
will.
And I think we're also going to be doing an activity, like matching kind of thing. So I'll post that and then you can try it out as well. Okay? Sound good? Cool. Anyone else leaving me? You're skipping it? Good. Good choices. You're leaving? Yes. Why can I not?